Welcome back. This is lecture number 7 on the series of lectures on metric spaces. Today we are going to end with the limit points and start with convergence of sequences. You will see how the limit point concept leads us to the concept of convergence of sequences. Yeah. So let us start the work. Yes. Just before that, I have to do that. Okay. Yes. Yeah. Right now I can share the screen. All right. Okay. Now let's do that. So what we saw last time was if A is a subset of a metric space, then A is closed if and only if A contains all its limit points. Okay, this was a theorem or a proposition or whatever it is, we proved it. Okay, it's done. All right. But let's try to understand the concept of limit. Recall, when do I say X is a limit point of A? Maybe I should say my thing. Okay. Limit point of A. If for every R positive, BXR intersection A is not empty, right? Right. Notice that R could be anything positive. Therefore, obvious thing is what happens if I choose R smaller and smaller. So obvious choice for such R will be 1 upon n. Therefore, if I take Bx 1 upon n for any natural number, then it should intersect A, right? That means there is a point A in this set, in this intersection, which I denote by an because an will be in bx 1 upon n. Therefore, this would depends on n, so I call it an, right? Now I have a sequence an, where this is a sequence in A, right? Now, if an belong to B except x 1 upon n, what does this mean? This if only if distance between x and an or an and x is less than 1 by n. Right? Distance between an and x is less than 1 by n. Now, do you remember our first lecture? How we started motivating the concept of metric on an arbitrary set? Now you should immediately understand what it means. What does it say? I give you time to recall first lecture. First 5 minutes of my lecture, in the first lecture. What does it say? It says, in some sense, the sequence an seem to converge to x. Note that we still have not defined the convergence of a sequence in a metric space. But our motivating thing, okay, talk in the first lecture should make us guess that in some sense an converges to x. Do you follow that? Yeah? Okay. So this motivates the definition of sequence. Okay. So let xn be a sequence in a metric space xt. I am sure all of you know what is meant by a sequence. I already defined. It's a function from natural number to the set x, and x at n we denote by xn and call it as an infinite tuple x1, x2, xn, etc., etc. This infinite tuple, so I denote by xn. Okay, this is in conformity with, okay, if I have a finite ordered n tuple, this is what I write. See, this sequence is also an ordered infinite tuple. So I write it instead of the very prevalent this notation, because nowadays this curly bracket is used for sets. Therefore, it's a constant sequence. This set, this I think of it as a set that consists of only one element. So I don't use this. See, I'm just justifying why I'm using ordinary bracket. Okay. If you don't want to ignore, ignore. Okay. So when do I say let x be a point in x? When do I say xn converges to x? That is, we read it xn converges to x. Notice that again, let me repeat, I am not saying as n tends to infinity, etc. Do you understand? This is just a concept for me. Xn converges to x. This is the notation. There is nothing like as n tends to infinity. Even though once in a while, because I was also taught like that, I may say x and converge to x as n tends to infinity. But for the definition, that does not come into picture at all. There is nothing like infinity, etc. We don't do that. Okay. If it's slightly confusing, though, don't worry, you will get used to it. So I will simply write it right. So I will not, I will write x and equal to x. I will not write as what you see in textbooks. I won't do that. Okay. So when do I say x and converges to x? As in the first lecture, we will make the definition of convergence of real sequences. So what does that mean? If for any given epsilon positive, there is a natural number n, so that for any n greater than or equal to n, the distance between x and x should be less than epsilon. Okay. Usually in MTTS, we write like this. There are so many bracket. 1, 2, 3, 4 row. So if x and converges to x mean for every epsilon, something must be true. So fix an epsilon, what must be true? There should exist a natural number, so that something must be true. So now epsilon is fixed. You had also found an n, capital N. Then what must be true? For every natural number n greater than or equal to capital N, something must be true. What must be true? Distance between xn and x is less than epsilon. Notice that this is like analytical because you are using inequality, but you can also make it geometric. For all n greater than or equal to n, it belongs to the open ball Bx. Okay. So what is the picture? It's very easy. Okay. So this is my x and these are my xn's. Sorry. If n is greater than or equal to n, okay, all my xn's will lie here. This is the radius epsilon. Okay. Do all of you understand the definition? Okay. Let us understand this definition going back to our earlier example. So what did we see? We saw that if x is a limit point of a, then there exists a sequence an, right? With what property? So that an belongs to bx 1 upon n for every n. Okay, this is what we observed. What does this say? This says that distance between an and x is less than 1 upon n. You understand that? So therefore what we have proved is if x is a limit point of a, there is this sequence an in a. You understand? I should have written that. There is a sequence an in a. Okay. So that an converges to x. Okay. Why an converges to x? Because if you give me an epsilon positive by Archimedean property, there is a natural number n, so that 1 upon n will be less than epsilon. You understand that? Therefore, if n is greater than or equal to n, you can see bx 1 by n is a subset of bx 1 by n. And that in turn is a subset of bx epsilon. All right. Therefore, for all n greater than or equal to n, my xn lies here. That means for all n greater than or equal to n, xn lies in bx epsilon. That is distance between xn and x is less than epsilon. Do you understand this? So what have we shown now? So what have we shown is if x is a limit point of a, then there exists a sequence an in a such that xn converges to an converges to x. Yeah. Okay. So pause, review, proceed. The converse is also true. What is the converse? Suppose A is a subset converse. Suppose A is a subset of x is a point in x, is such that there exists a sequence an in A such that an converges to x. Then what do you want to claim? Limit point of A. Proof is easy. Yeah. To prove it's a limit point of A, what do I have to do? You give me any R positive. I have to show BXR intersection A is not empty. This is what I have to show. But remember, since an converges to x and take epsilon equal to r, this is positive. Therefore, I know there is a natural number n. So that for every n greater than equal to capital N, distance between an and x is less than epsilon equal to r. That means for every n greater than equal to n, my an lies in b, x, r as well as in a. So I have produced elements of a which are in this. Okay. So we can say that x is a level. Okay. So what have we proved? We have proved a theorem. A is a subset of x, a metric space. X in x is a limit point. A, if and only if there exists a sequence an in A such that an converges to x. Okay. Pause, review, proceed. So this is all we have proved. Okay. Now, as usual, what we plan to do is now let us look at convergence of sequences in our list of examples. Okay. First, examples now. R, x equal to R. This is as usual. There is nothing wrong. It's the same, right? What does it mean? If I have a sequence of real numbers xn, when do you say xn converges to x? If for every epsilon greater than 0, there is a natural number, so that for every k greater than or equal to n, modulus of xk minus x, that is xn minus x, is less than epsilon. Okay. This is nothing other distance between xk and x, less than epsilon. This is same as saying xk lies in the interval x minus epsilon 2. So a sequence of real numbers converges to a real number if and only if it converges in the metric space. Okay, there is no difference. But when it comes to x equal to Rn, very interesting thing happens. Okay, since to see if I have a sequence here, let us make it as a something like a yeah, let us make it a sequence. Then I will think of a sequence as xk. Now xk, maybe I will call it as a vk. Okay, vk is an element of Rn. Therefore, vk is a vector, so I should think of it as x. It has n coordinates: xk1, xk2, xkn. You understand this? Yeah, that's how I would write. And now, suppose v is a vector in Rn. I want to know when does vk converge to v. You follow that? Just because this n is there, I don't want to. Other way, maybe I have to use capital N, or I might use a little m. But then when you want to talk about some Cauchy sequence, etc., I may need n and m also there. Okay, so it's best to get used to that. Okay, running index for a sequence is k now. For in the case of Rn, that will be easier for us. Okay, whatever I want to do is very simple, based on a very simple observation. So I would like to make this. So when does vk converge to x? According to our definition, given any epsilon positive, there is a natural number n, so that for every k greater than or equal to n, distance between vk and v is less than epsilon. Okay, what is our d? D could be either d1 or d2 or d infinity, because I need a metric, right? Where d is d1 or d2 or d infinity. But you are once and for all fixing it. Okay, take d2, d1 or d2 or d infinity, whatever it is. But just keep it fixed so that these things will make sense. You understand? Yeah. The very first observation I want to make is the following. Okay, very general. We had already made it somewhere, but it's worth repeating. Suppose u and v are vectors in Rn. and let u equal to u1 to un and v equal to v1 to vn, then you see that ui minus v an absolute value, okay, for every I is less than or equal to distributed in u and v. Do you understand this? This is true for every I between 1 and n. Yeah. Why? Because either it is something like mod x ui minus vi 1 to n. Therefore, mod ui minus vi is less than or equal to this. Or ui minus vi. And here I have maximum of mod ui minus vi, maximum running from 1 to n. Therefore, in that case also, or it's the distance is going to be summation mod ui minus vi whole square power half, right? But this fellow is greater than or equal to mod ui minus vi whole squared and to the power half, but that's equal to mod ui minus vi. You follow that? Therefore, the crucial observation, let me again write it. Therefore, for every I between 1 and n, the ith coordinate difference in modulus will be less than or equal to distance between u and v. What is this d? D could be either d1 or d2 or d infinity. I don't care which one, whatever it is. Okay. This immediately should suggest something to you. Suppose my vk converges to v, right? Then let us look at, okay, now vk is vk1, vki, vkn, and v is v1 to vn. You follow that? See, this v1 to vn should not be constructed with a sequence now. It is only the ith coordinate of v1 to vn. See, there is always this problem. Okay. If you're a beginner, you may get confused. This is not a sequence now. These are all real numbers. Okay. Whereas this vk is sequence. See, so you follow that? Yeah. So let me call it something like it converges to x. Therefore, let me call it as x1 to xn. Okay. Suppose vk converges to x. Then what happens? I write vk as vk1, vki, vkn, and this one is x1, x2, xi, xn. Right? Then distance between vki, that is sorry, mod vki minus xi is less than or equal to distance between vk and x. This is by this. Do you follow that? This is true immaterial of which k you chose and what all I between 1 and n. You understand? Therefore, if I fix I between 1 and n, what does this say? If I fix an I, then I have a sequence. How do I get a sequence of real numbers? Just to make sure you understand, let me write it, because if you're a beginner, it's good to see these things pictorially. My V1 is going to be V11, V1I, V1N, and my Vk will be Vk1, Vki, Vkn. You understand? Now my V is going to be, sorry, my X is going to be X1, Xi, Xn. Now what did we find? If Vk converges to X, this distance goes to 0. That means mod Vki minus Xi should also go to 0. Do you understand? That means this sequence of ith coordinates converge to the ith coordinate of X. Do you understand this? Okay. If you are slightly confused, let us stick to R2. The sequence, let us call is now X and Yn. And I want to know when does it converge to, suppose this is given. This is given. Right? Then what do I know? Xn minus X is less than or equal to distance between Xn, Yn and Xy. Right? So if you give an epsilon positive, there is a natural number n, so that this fellow for n greater than or equal to n, this fellow is less than or equal to epsilon. That means for all n greater than or equal to capital N, mod xn minus x is less than epsilon. Similarly for yn minus y. That means xn converges to x and yn converges to y. What does that mean? That is, if the vector x and yn converge to the vector xy, it implies the convergence of coordinates. The x coordinate Okay, the sequence of x coordinate converges to the x coordinate. The sequence of y coordinate converges to the y coordinate of the limit. Do you understand this? And for which metric we have proved? For all the three metrics we have proved. Okay, so let me make it a general thing. So what you have proved is this: if vk converge to x, then the sequence of ith coordinate vki converge to I, the ith coordinate of x. This is true for every I between 1 and n. Okay, pause, review, proceed. What is the next question you would like to ask? Whether the converse is true, right? But that's actually again easy. Okay, I can give a direct proof, but as I said here, what did the whole thing depended upon? This proof of this statement depended upon only one simple observation. What was the observation? That was this observation. Right? The same observation or rather similar observation is going to prove us the other way around. What is the question I want to ask now? I want to ask the converse. Okay, let me stick to R2. Okay, notation it will be easier. Okay, suppose I know I have a sequence x and yn and a vector xy, and okay, given the hypothesis xn converges to x and yn converges to y. Now you don't ask me where it converges in R. These are sequence of real numbers, and on real number we have the usual absolute value metric. So with respect to which it converges. By example 1, we know what it means. Right? Now, what is the question I want to ask? Does the sequence of vectors x and yn converge to the vector xy? Yeah. So how does this follow? Is it true? Okay. Again, it depends on a very crucial observation. Right? Let us prove that. Okay. So suppose I have a vector, let us say x and y, or u and v, two vectors in R2. This is again on Rn also, it's the same thing is true, but for some, okay, maybe do it, let me do it in Rn. Suppose u equal to u1 un, v equal to v1 vn. Suppose I know how to estimate ui minus vi for all I. Okay, we know how to estimate. Then question is, can we estimate distance between u and v? Do you understand? So when I say x and yn converge to x, that means I know how to estimate mod xn minus x, mod yn minus y, but I want to estimate distance between x and yn and distance between x and y. Distance between x and yn and xy. Okay, I know how to estimate mod xn minus x, mod yn minus y. Does that allow me how to estimate this? That's a question I'm asking. Do you understand this? But if you think carefully, you will know it's very easy. Yeah. Suppose I know how to estimate this, okay, for all I, then I know how to estimate distance, yeah, between u and v, because there's going to be a maximum of mod ui minus vi for 1 less than or equal to I less than or equal to n. Right? Suppose each one of them is less than epsilon I, then this will be less than or equal to maximum epsilon I. Right? So I know how to estimate. Just this way of thinking is never emphasized in textbook. They immediately start writing a proof. Okay. But my purpose is always to understand why certain things work, how to think on your own also. Okay. And let's look at D1 of U. Then that is going to be mod x, mod ui minus vi. But I know how to estimate each one of them. So this will be less than or equal to summation epsilon I want to n. So I also know how to estimate. Yeah. And how about D2 of uv? Now I know all of you will know this is ui minus vi whole squared to the power half. That will be summation epsilon I squared to the power half. So In some sense, once I know how to estimate these things, I know how to estimate. Okay, please pause, review, proceed. Please go through it. Do not get intimidated or flustered. Do not get confused. Just understand the basic principle. Even if the nitty gritty you are slightly worried, second time reviewing will make you understand better. Okay, but try to understand what we are aiming at. We are aiming at, if I know how to estimate mod ui minus vi for each I, do I know how to estimate the distance between two vectors u and b? That's the question. Okay, now we are going to think of this idea. Exactly not this which is going to work, but you will see this idea helps us to understand what is happening. So let us prove. Let us assume xn converges to x. I am back in R2 for simplicity. Okay, the proof actually works in any n and yn converges to y. Okay, then what do I want to do? I want to estimate xn minus yn. See, so I want to prove xn yn converges to xy. This is what I want to prove. So to prove this, what is it I have to do? You are going to give me an epsilon positive. Then I have to find a natural number. Then something happens, right? So let epsilon be given. So I will not worry about n, etc. But what will I worry about is I want to estimate this. So between in d1 of, okay, let me call it as a u and b, un and vn, so that I don't write u and vn, x and yn, etc. un, vn. Okay, this is summation. D1 metric will be summation. Okay, mod xn minus x. This is v. This is un. Let us call this as u. Un minus plus mod yn minus y. Right? I want this to be less than epsilon. Do you understand this? I want to show un converges to u. That means I have to estimate the distance d1 distance between un and u. I want to show this less than epsilon, but I know that's equal to this. I want, okay. So if I want to make this less than epsilon, what is the easy way out? I can make this epsilon by 2 and this also is epsilon by 2. There is no sanctity. I can make it epsilon by 3, this 2 epsilon by 3, or I can still make it epsilon by 3 also. Then the whole thing will be less than 2 epsilon by 3, therefore this. Are you following? So anyway, for symmetry, we will assume I want to make. Do I know how to make this? Yes. How do I do that? Since xn converges to x, there exists for this epsilon by 2, there is an n1, so that for every n greater than equal to n1, mod xn minus x is less than epsilon by 2. And similarly, there is an x2, so that mod yn minus y is less than epsilon by 2. But I want it to be true for every n greater than equal to some capital N. So what do you think I will do? Take n equal to maximum of n1 and n2. Do you understand this? Yes? Okay. So I have proved it in D1. Okay. Right. Now D infinity is similar. What is D infinity of u and u? That is maximum of mod x1 minus x, mod yn minus y. But let's keep the same notation. Okay. So I know there is an n1, so that for all n greater than equal to n1, this will be less than epsilon by 2. For all n greater than equal to n2, this will be less than n by 2. Therefore, if I take n equal to maximum of this will be less than epsilon by 2. Yeah, because each one of them is less than epsilon by 2. I want to show it's less than epsilon, so but I have proved this. Are you following? Okay. Now let's look at D2. This is, so let us look at its square. So I want to show this is less than or equal to epsilon squared. Yeah. Remember my earlier thing. If a and b are non-negative, then a is less than or equal to b. If only if a squared is less than or equal to b squared. How many times we have used? We are going to use this, right? What is this fellow? D2 squared of u n u. This is xn minus x whole squared plus yn minus y whole squared. I want this to be less than epsilon squared. So again, I can make this epsilon squared by 2, epsilon squared by 2, right? How do I make it? Since xn converges to x, as usual, there is n1, so that for all n greater than equal to n1, mod xn minus x is less than something Remember, I want to square, therefore I can take it epsilon by square root 2. Therefore, square will be less than or equal to epsilon squared by 2. Do you follow that? And similarly n2. Therefore, again, same trick, you take n equal to maximum n1 n2. Okay, I went pretty fast here, but because if you are watching my video, you should learn to think along with me. And more than that, even if you understood only 30-40%, you should have confidence in yourself that you can do on your own. You don't need comparison for that. Okay, so let us recall. So let us make it as a theorem. What we have proved? I have a sequence Vk in Rn. Okay, then Vk converges to Vk converges to X in Rn if and only if for each ith coordinate Vki converge to Xi. Where Vk is Vk1, Vki, Vkn. This is if and only if. Okay. So just make sure you understood this. Okay. All right. Now comes the next example. Suppose my xd is a discrete metric. Do you remember that? Yeah. Now suppose I have a sequence xn and assume xn converges to x. What does it really mean? Now you should immediately see that, right? What happens? The moment I take epsilon equal to 1, there exists an n. So that for every k greater than or equal to n, distance between xk and x should be less than 1. Remember, distance between any 2 points is either, if it is not 1, it has to be 0. That means distance between xk and x must be 0. This is true for every k greater than or equal to n. You understood that? So what does it say about the sequence? It says the sequence will be like this. x1 up to xn minus 1 can be anything. After that, it will be just x. It's a constant sequence. Eventually. Let me write it. Eventually. Constant sequence. What is meant by, therefore, if xn converges to x, okay, put a thing after certain stage, everything must be the same constant. What constant? The so-called the limit of the sequence. Do you follow that? Okay. Right. Now let's come to subsets. Suppose A is a subset of xd and D is the induced metric on A. Then I have a sequence A in A and a point A in A. When does A n converge to A? In A, if only if A n converge to A in X, in the metric space AD, in the metric space XD. This is very easy, right? Just convince yourself. Okay, if you give me an epsilon positive, there is a capital N, so that distance between A and A is less than epsilon. But that distance is the same as the distance A and X. It does not matter which t. Therefore, the result follows. Right? Okay. Now there are two more examples. The other example is I have a metric space XD. I also have this B metric, beta metric. Okay. Now I say xn converges to x in the metric D, in the metric space XD, if and only if xn converges to x in the metric space x beta. That's very obvious. How many of you see that this is obvious? Yes. So what are you going to give me? Suppose I want to show, let's assume one way. Okay, let us assume this. Okay, this assume, and I want to prove this. Okay, the other way around is also easy. Suppose x and converges to x, I want to prove this, right? So you are going to give me an epsilon positive then I have to say there exists a natural number n so that the between xk and x is less than epsilon, because this is the distance. I want to prove this. This is for every k greater than equal to n, right? Now what do I know? Now suppose epsilon is greater than 1, right? If x is greater than 1, then beta of any 2 points x and y is less than equal to 1. You understand that? Are you following? This is same as saying xk lies in bx epsilon, alright? But if epsilon is greater than 1, we already saw b beta of x epsilon for epsilon greater than 1 is nothing other than the full space. Therefore, certainly, I do not even choose an n. For every k, xk will lie here. This is for every k natural number. Do you understand this? Please pause, understand, review. Okay, so therefore the important thing comes only if epsilon is less than or equal to 1. Okay, if epsilon is less than or equal to 1, then we have seen b beta x epsilon is same as b del d of x epsilon. Okay, now again and again, do you understand why we spent 1 hour to understand what are the open balls in various metric spaces? You see that it comes to a rescue. Okay, if I just define open balls and then went ahead, then you will struggle here. Then I have to recall, review. It will look like new things, whereas it's an old hat now. I know that. I had already seen it, so it's easy because we already used it at many places to prove open balls. A set is open in x beta if only if it's open in xd. There also we use this fact. You understand that? Now it's easy, right? So suppose I want to prove this beta, then what will I do? Since xn converges to x in xd, and for this epsilon there is a natural number n, so that for every k greater than equal to n, my xk lies in b d x epsilon. But that means xk lies in b beta x epsilon because epsilon is less than equal to 1. That means xk converges to x in x beta now. Okay, pause, review, proceed. The last example is a source product metric space, but it's very easy. Suppose xd is symmetric, yd is symmetric, and we have x cross y, and with d is the product metric. What is our product metric? You know that it's a maximum of d of some the x coordinates and d of the y coordinates, and where d is the distance on x, this d is the distance on y. You okay? I do not, as I said earlier, I do not write it as d sub x, d sub y, because I think all of us are intelligent. Okay, so I want to say this. This is again easy. Okay, this is exactly similar to the way we did d infinity on R2 or Rn. Why? That is, take a sequence x and yn. Okay, when does it converge to xy? In the space x cross y d. This is what I want to understand. What I am claiming is this happens if only if xn converges to x in xd and yn converges to y in yd. That's it. This is our claim. The proof is easy. Okay, let us assume this. Okay, let me prove this. Let me xn converges to x, yn converges to y. Then I want to prove x and yn. You can see the proof. Therefore, I have to estimate distance between x and yn and the distance between x and y. But what is this? This is the maximum of distance between x and x and distance between y and y. So I want to show this is less than epsilon, right? But what do I know? Since xn converges to x, there is an n1, so that for n greater than or equal to n1, this will be less than epsilon. And similarly, there is an n2, so that for all n greater than or equal to n2, this will be less than epsilon. Therefore, I take n to be max of n1 and n2. For any n greater than or equal to capital N, this will be less than epsilon. This will be less than epsilon. Therefore, maximum will be less than epsilon. That means this will be less than epsilon. So we proved this. The other way around is very easy. Okay, if right, see if x and yn converge to xy, okay, this is all right. Pause, review, proceed. Other way around, x and yn converge to xy. Does that imply x and converge to x and yn converge to y? That's very easy because I have to estimate dx and x, but notice that that's less than or equal to maximum of dx and x and dy and y, but that is d of x and y and xy. Since this is given, I want to show this less than epsilon. Since this convergence takes place, there is an given an epsilon, there is an n, so that this will be less than n for every n greater than equal to n. That means for every n greater than capital N, this will be less than epsilon. Okay, so we proved it. Okay, so there is a last thing which is usually what everybody does. Suppose I have a metric space xd. Okay, I want, and suppose can it happen xn converge to a and xn also converge to b with a and b distinct? Can it happen? You must have seen it in real analysis. If xn converges to x and xn converges to y, then x equal to y. You call it the uniqueness of the limit, right? Usual proof is something slightly different, but I want you to understand the proof in a slightly more geometric way, which will also allow you to learn topology when you go to learn topology. Okay, the basic idea here to prove we want to claim a equal to b, uniqueness of the limit. Okay, this is what is called uniqueness of the limit. By the way, this, okay, if xn converges to x, x is called the limit. Okay, x is called a limit of the sequence xn. Now what we want to say is I can replace a by the because it's unique. Okay, let us prove that. The basic idea is the following. Suppose you give me 2 points a and b in a metric space xd, and if you say a is not equal to b, then I want to say there is an r positive so that bar and bbr, their intersection is empty. Again, try to imagine this. I have this. Okay, I have 2 points x and y. Then what I want to say, there exists an open ball around this. They are supposed to be the same radius. Okay, they do not look like anyway. This is your a and this is your b. I can separate them by means of open balls. Okay, right? How do you prove that? So what you do is, as I said, work backwards. Suppose BAR intersection BBR. Okay, I want, suppose x belong to this, right? So picture will be like this. This is a, this is b, and there is an x which is common. This is a b, right? Then I know how to estimate distance between a and b. Distance between a and b will be distance between a and a plus distance between x and b. You understand that? And where does this belong to? This will be, this is less than r, and this is less than r, right? Therefore, what happens? Distance between a and b is less than 2r, right? That is, distance between a and b or 2r must be greater than distance between a and b. So what does it suggest? If the, if r is said that br intersection bbr is not empty, then the 2r must at least be distance between a and b. That's what we understand. Therefore, I don't want this to happen. So what should I do? I can choose r such that 2r is less than or equal to, let us choose r such that which is less than or equal to distance between a and b by 2. Can I do that? Remember, A is not equal to B, therefore distance between A and B is positive, therefore this is a positive number, right? So take any number R which is less than. In fact, you can take equal to also, but for convenience sake, I'm not doing. Is that okay? Now, suppose this is my R, then what happens? If X belongs to these two things here, then distance between A and B will be less than this, less than this. But this says 2R, but this says this is less than distance between A and B. You understand? So this is a contradiction. Are you following? Did I go fast? Yeah, I tried to arrive at an R. Now that I arrive at R, I'm using the same inequality. Okay. Suppose if I claim this is empty, for this R, we claim is BR intersection BBR is empty. Okay. Suppose not empty, there is an X common. That means the distance between A and B, okay, will be distance between A and X and distance between X and B. This is always true for any X. Do you understand my thing? The triangle inequality is power, the curry leaf. This X is a curry leaf. I can choose anything. I am going to choose X, the curry leaf, very smartly. That is this common X. But X belongs to BAR, therefore it's less than R. X belongs to BBR, therefore X is less than R. Therefore it's 2R, right? That means 2R is greater than DAB. But by our choice, 2R is less than DAB. That's a contradiction. Therefore, this is true. Okay, now come back. Now suppose my Xn converges to A and Xn converges to B and A is not equal to B. I claim A is equal to B, suppose not. Then what do I know? As earlier, there exists two open balls R so that BR intersection BBR is empty, right? So I have this, right? Or maybe I have a picture earlier, right? Now I have sequence Xn, right? Now notice that since Xn converges to A as well as B, there is an N1. Okay, if n is greater than or equal to n1, my Xn should lie here. If and similarly, since Xn converges to B, for n greater than or equal to n2, Xn should lie here, right? Now there is a dilemma. If n is greater than or equal to maximum of n1 and n2, or take n equal to n1 plus n2, then n should lie, Xn should lie here, Xn should lie here. So it will wonder where should I lie, because they are not common. They don't have any point in common. Do you understand that? Yeah. Let me just complete the proof. If Xn converges to A, there exists n1 so that Xn lies in BR for n greater than equal to n1. And similarly, Xn converges to B, there is n2 for n greater than equal to n2. Xn lies in BBR. Therefore, I take n equal to n1 plus n2. Then Xn should lie in BAR. It also lies in BBR, but this is the empty set. We have just now checked. So this contradiction shows A must be equal to B. Okay, the usual proof you see will be like this. Okay, distance between X and Y is less than between distance between A and B. Sorry, A and B is less than or equal to distance between A and Xn plus distance between Xn and B. As n goes to infinity, okay, do you remember? I usually don't use that word. This goes to 0, this goes to 0, therefore distance between A and B goes to 0. That means distance between A and B is 0, and hence A equal to B. That's the usual proof. But this is much more geometric proof. It actually tells you what goes wrong. Okay, so this is called the uniqueness of the limit. So I think we will stop here. Okay, and this is good enough for you to get work with this. Okay, there may be few other things which I can do, but as I said, this series of lectures I want to be very basic concepts in metric spaces. Start with metric, open sets, open balls, closed sets, right? And then limit points, sequences, their convergence. What is next? Continuity. Okay, so We will define continuous functions. We will look at continuous functions, look at all these examples and prove few results about continuous functions. And for the time being, the series will stop. Okay. So my guess is at most two more lectures. We will stop the, okay. It will be temporary break. If necessary, I will resume more later. Like I may want to talk about density, this and that, closure of a set. All those things can come later. But these are the very basic. If you have learned all these things, I think you should feel very comfortable in your wherever metric space are needed. Okay, I hope you enjoy. Thank you very much. Let's meet again sometime.